Hi everyone. In this video, I am going to give you the definition for the common ion effect. We're going to see how it applies to previous concepts that we've learned before and apply this to an acid-base reaction problem. This is the problem actually. We want to figure out the pH for an acidic solution, but then in part B, we're going to take the same acidic solution and add what's called the common ion and see if the pH changes. So these are the two problems we are going to do, but first I want to give you a definition for the common ion effect. Common ion effect is the tendency for a common ion, an ion that you see in more than one process, and you combine those two processes, to decrease the ionization of a weak acid or weak base. So this definition is pretty focused on acid-base reactions, but later we'll apply this. Later in this unit, we'll apply this to the solubility of an ionic compound. You've seen this before, or you know this because this is very related to Le Chatelier's principle. Le Chatelier's principle. Let's take an equation, a general equation of a weak acid. Let's say we have HA plus water in equilibrium with the hydronium plus this A minus. So this A minus is potentially a common ion. Because what if I add let's say a lithium anion. Not lithium anion, but lithium plus the anion. So it's a salt. And it's neutral because lithium is +1. In this case, anion is -1. You are going to understand that any lithium salts fully dissociate. So what happens is this fully dissociates into the Li plus the A minus, and you notice that now we are, by doing this, by adding the Lia, we are increasing the A content. You can even think of it as increasing the concentration of A minus. When that happens, you know your conclusion is, because of Le Chatelier, you're going to shift to the left to compensate for that added A minus, the common ion. And what's going to happen? When you shift to the left, you create less hydronium. So you are shifting to the left, you are consuming H3O plus, your pH goes up, or let's say you become less acidic, and the pH goes up. That is the common ion effect, and it is decreasing the ionization of a weak acid in this case. Let us go ahead and tackle those two parts of a problem. Well, this is section B. Okay. And we are applying the common ion effect to an acid-base reaction. Okay. The first problem is not showing the common ion effect. It's just a straight up, what is the acidity, no, what is the pH of an acid solution? Part A. Remember how to do this? When in doubt, maybe not even when in doubt, to have a clearer picture of what is happening, draw the chemical equation. You have acetic acid, in water, and it's acidic, so you create the H3O plus, and the anion is actually acetate. Now, if you want to know the formula, before we do the formula, in general, what are we doing? HA plus H2O goes to H3O plus here's your A minus, the potential common ion. And if you need the formula, C2H3O2, and it doesn't matter where you put that acidic hydrogen proton, either at the beginning or at the end, plus water goes to H3O plus, now we have the anion, C2H3O2 minus. Okay, we have a Ka. Yep, we do have a Ka, 1.8 times 10 to the minus 5. We're setting up an ice table because we're given an initial amount of acid, ICE, but we're not given the molarity. We are given the moles and the liters. But the liters is 1, so moles divided by liter gives you molarity. So this ice table, I just want to always remind myself that we're using molarity. This will be a little more useful when we do more challenging problems with titrations and buffers. But anyway, our molarity now is 0.10 molar. Just taking 0.1 divided by 1. Water doesn't matter because water's liquid. It is not involved in the equilibrium expression. 0, 0. I'm going through this kind of fast because you've seen this before. Oh, this is plus x plus x. Okay, there is your complete ice table. We have a Ka. It's 1.8 times 10 to the minus 5. Normally, I would ask, when you're first learning this, you should draw out the expression using the components, using the compounds. Concentration of H3O plus times concentration of the anion, etc. But we've done this probably 10, 15, 20 times already. We know it's these two multiplied, x squared over 0.10 minus x. We'll use the x is small approximation because that is 10 to the minus 4 or lower, and the starting molarity is much higher. So the x shouldn't matter, And here we get x to equal 1.8 times 10 to the negative 5 equals, times 0.1 equals, take the square root of that, equals. Uh-oh, it's at small, 0.001342. Okay, so I have that number saved. To check if it's small, if it's less than 5% of the initial amount, divided by 0.1, okay, good, times 100%, 1.34%. So that's valid. You know that x is this x right here. This is a molarity, and it's equal to the H3O plus concentration. Therefore, the pH equals the negative log of this number. Oh, I lost that number. 0.001342 equals the log of that number times negative 1. Ooh, pretty low. 2.87. It's a weak acid, but the pH is pretty low. That's because it's actually a high concentration. Okay? Normally, with acids, you use much lower than 0.1 molar amounts. That's part A. Part B. Look what they're doing in part B. They are adding sodium acetate. Sodium acetate is Na, C2H3O2. So that anion is minus, but it's paired up with a positive cation. But we know that it's going to break up because this is the salt of a group 1 metal. Those fully ionize, fully dissociate. So we do get Na plus C2H3O2 minus. See? By adding that salt, sodium acetate, we're doing this trick. We're adding more anion, we're adding more common ion. It's going to shift to the left. So how do we set this up? We have our equation of the acid. Same equation that we used for part A. But the twist is, let me just get the concentration of the acetic acid. That is straight up the same as what we've done before. Just take the moles divided by the liters. Nothing happens initially. This is I's initial. Nothing happens initially to that acid. You literally dissolved that much. Part B is saying you did the same thing. You're doing the same type of solution. So that was 0.10 molar. So here's the twist. We don't have H3O plus initially, okay, before this dissociates, but now we have that added common ion, which is sodium acetate. We have 0.050 moles, but we're still in 1 liter. Okay, so this is 0.050 molar. Now, is that going to mess us up when we're trying to solve for x? I don't know. We have to go ahead and work out the problem. So now we have a minus x. Okay, let's see how much this dissociates. The weak acid. Water, again, doesn't factor in. This is plus x. This is plus x. Same thing we've done before, but now we have 0.10 minus x. We have x, but here we have 0.050 plus x. Now, you may wonder, well, how do we know that it's plus x? How come we're not minusing x in this case? That's because in our Ka expression, we have H3O plus in the equilibrium expression. So that cannot stay 0. That cannot stay 0. You have to add to the H3O plus. Okay. Now, it's a little bit tricky to wrap your head around because Le Chatelier says that we are going to shift to the left. Well, that's true that we're shifting to the left in relation to the reaction where it didn't have the common ion, or it didn't have the common ion. So the idea here is that we actually do this reaction and we let it come to equilibrium, and then we add the common ion. It actually doesn't matter whether you add the common ion at the beginning or at the end. You're still going to establish an equilibrium. Okay? Eventually you are going to get to the same place. The problem here says you're just adding everything together, which is perfectly fine. But when you think about Le Chatelier and you're trying to wrap your head around, well, how do I know that it's shifting? Well, Le Chatelier says, well, you have an equation at equilibrium, and then you shift. But we're not doing it that way. We're throwing everything at the same pool and realizing, again, that this has to be plus x. You have to make H3O plus. But we're going to see, we're going to see in a bit that we actually did, give me 1 second. We actually did decrease the H3O plus concentration in relation to what we got for part A. Oh, that was very convoluted. Sorry about that. But this is a setup. Okay. Ka is still the weak acid. You still use its Ka. But now we have x times 0.050 plus x going, over 0.10 minus x. Now we're going to use the x is small again. And we get rid of any time you plus or minus x, or anytime you plus or minus 2x, or anytime you plus or minus 3x. You know, that x is so small it doesn't matter if you subtract or add 1, 2, or 3 of those. Now this x we do have to keep. This x we do have to keep. We're not subtracting this x. But essentially, this term in parentheses is 0.050, and this term in parentheses essentially is 0.10 because x is essentially close to 0. Okay. What that does, it simplifies, and let me try to do this in my head. Not in my head, but without writing anything down. 1.8 times 10 to the negative 5. Okay. And we're cross multiplying. So times 0.10. But now up here we have 0.050x. So do you see how we have to divide both sides by 0.050, and we get a new x. The new x, 3.6 times 10 to the minus 5. X equals 3.6 times 10 to the minus 5 molar. The pH equals. Now without the common ion, the pH is 2.87. With the common ion, we take the log of that answer times negative 1. It went up 4.44. Compare those two numbers. This is less acidic. It has less H3O plus than if we didn't have the common ion. Okay. Let me just write this H3O plus. Now what happened to the common ion? You know, in the common ion, in the first part where we didn't artificially add it, we had still x, right? That x there is still 0.001342. In this case, we take 0.050 plus x 3.6 times 10 to the minus 5. So essentially, it didn't change from the amount that we initially added. Okay, so very, very little actually went forward, but still some went forward because we do have to create H3O plus to satisfy the equilibrium constant. Okay, that is the common ion effect, and we solved this problem. So watch out for that. Watch out for an acid-base reaction where you're solving for the pH. Watch out if they add sodium and the anion or lithium anion salt, because you're going to put a number in this position right here. This will not be 0 anymore.